So in today's discussion, we're gonna go over the how to sketch a Bode diagram for a given transfer function. And before we start, I just want to emphasize that we plot Bode diagrams or we sketch Bode diagrams only for stable or marginally stable system. If we have any right half plane poles, then the system is unstable, right? And we will not be able to plot the Bode plot. Or like if you give MATLAB something that has an unstable pole, it's going to give you a plot, but that plot does not make any sense, and it's not related to, like, we cannot use it for analysis. Okay, so I just want to emphasize that Bode plots are defined for systems that do not have right half plane poles. Okay. Okay, so the first step for plotting the or sketching the Bode diagram is that we put the transfer function in the so-called normalized factors form. Okay, which is quite simple. Like when you have something that is s plus tau or s plus anything, right? You just factor out the tau so that you get a factor of this form, 1 plus 1 over tau times s. Okay, and then you have the tau outside. If you have a second order factor, you factor out the free term, which is omega n squared, and you end up with something like this, which is 1 plus 2 times zeta divided by omega n times s plus s squared divided by omega n squared. So and the if you have a pole at the origin, they remain the same. Okay. So let's try to apply that to our transfer function. On top we have s plus 2, so we factor out the 2, right? Then you get 1 plus half s, and then we have a 2 here, right? Then below we have s plus 10 and s plus 30, s plus 2,500. So we factor out 50 squared, which is 2,500 over here, and 10 as well. We end up with these two factors. And then we just carry out the division and multiplication over here, which simplifies to, this is, it's not 1, this is 6. So when we carry out the simplification, you end up with a factor of 5. So this is the gain k. And the rest are the factors that we have, which is 1 plus 0.5 and 1 plus 0.1 s, and then the second order factor here. Any questions? Okay, so this is the first step. The second step is that we basically we sketch the Bode plots of each of these individual factors. Okay, and so the Bode plots, as you know, consist of two things: the phase of the factor and the magnitude of the factor as a function of the frequency. So, for instance, if we have a pole at the origin, basically, which is 1 over s, right? Then we know that its magnitude is going to be a line that has a slope of negative 20 decibels per decade. You guys know what a decibel and a decade is, right? Okay, so and it passes through the point 1, right, on the horizontal, like 1 and 0 on the horizontal axis, because if you put if you put 1 over I omega and then you put omega equal to 1, you get 1 over I, which has a magnitude of 1. So when you take the logarithm of that, you get 0. So it passes through the horizontal axis at the frequency equal to 1. Now, next, the phase, right? The phase of 1 over I omega. And we can see that like the phase, the phase of 1 over I omega is just going to be equal to the phase, um, the phase of negative I, because omega is just a factor that does not affect anything. So it's going to be equal to negative 90 degrees. So the phase of this factor is going to be a horizontal line passing through negative 90 and does not depend on omega. So this is the sketch for the you want the factor 1 over s, and this is actually an exact plot. Like this is exactly what the Bode plot for the factor 1 over s looks like. So the next factor is if we have a pole, right? A pole at s plus 10 in our case, which translates to 1 over 1 plus 0.1s. And so this factor, the plot or the Bode plot of this factor consists of several segments. The magnitude part consists of two line segments. The first one is horizontal. It passes through or horizontal at 0, okay, and then goes until the frequency 10, which we call the breakaway frequency. And then starts having a slope of negative 20 decibels beyond that. So this is a slope of negative 20 decibels per decade. And the phase consists of 3 segments. The first segment is from whatever where you started your Bode diagram, okay, until point 1 of the breakaway frequency, which is 10. And then it starts having a slope of negative 45 degrees per decade. Until it reaches the second point, which happens at 10 times the breakaway frequency, which is in this case 100. And then it goes back to 0, to a slope of 0 degrees again. So this is these segments are called the asymptotes of the Bode plot. And the Bode plot is not exactly on them, but rather it kind of tries to approximate them, or it approaches them in the limits. So the actual Bode plot is something like this. Is this dashed line? Okay. All right. Now Given that this is the shape of the pole, can someone tell me what is the what does the zero look like?
It's the same, but flipped over the horizontal axis.
Right. Thank you, Mark. So it's just a reflection with respect to um, the horizontal axis, which is the frequency, right? So in this, instead of going like this, it'll be something like this, and similarly, it'll be something like this. All right. Now we go to the third factor, which is the pole pair. Like when you have a pole pair that has a um, uh, second order form, normalized vector form. Similarly, the plot looks similar to the case of one pole, in the sense that we have two line segments, one starting at 0 until the breakaway frequency, and then negative 20. Um, and um, so this is actually, I think, is not negative 20, it's negative 40. Let me check that. And so, and the other, and this is the magnitude, and the phase is a horizontal line, right? Again, up until the um, 0.1 of the breakaway frequency, which is 50. So this is 5. And then a line of slope negative 90 degrees per decade. And then a horizontal line again at negative when we approach 500, which is 10 times 50. It approaches it approaches a 0 slope um, line. So this is negative 14. Can someone tell me why is this negative 40 and not negative 20? Any ideas?
Isn't it because it's a pole and not a zero?
It's a pole, right? But I'm asking why is it negative 40 and not negative 20, right? If it's a 0, it'll be positive, right? So the reason is that because we have two poles here, right? This factor has two poles. Each pole contributes a negative 20, and so we have two of them, so we get negative 40 decibels per decade as a decrease in this magnitude. Okay. So I may need to correct something later on, but that's okay. And similarly here in the phase, we get negative 90 degrees per decade because we have two poles. Each one of them contributes negative 45 degrees per decade. And the next thing to say here, or to notice here, is that there is a deviation from these asymptotes, and that deviation actually depends on the damping, and can be much larger if the damping is much less than 1. Now, given that a second order system uh, 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 given that a second order system with or has a very small damping, do you think what happens when the damping gets small to this? Like, what happens to this peak? Does it get bigger? Does it get smaller? Can anyone tell me?
It gets bigger.
And why is that?
Uh, I don't remember that.
Right. So do you guys remember that that famous example of the, don't recall the name of the bridge, but there was a bridge that was that broke down because of the wind, and it was oscillating, like the wind were oscillating or excited certain modes, the natural frequencies. Yeah, thank you, Robert. Yes, the Coleman arrows. It's exactly that's exactly what happens. Recall that the Bode diagram is the magnitude of the steady oscillation that happens when we give the system a sine input at the frequency given by the horizontal axis. Like, for instance, if we give this factor, right? If we give this factor a sine input, okay, of at a frequency of 1, so basically sine 1 over t, if we give it to this system, we will get a response that is approximately equal, that has a decibel approximately equal to 0. Okay, somewhere here. If we give it something at the frequency of 1000, this is 1000 times t, right? We will get something on this, or the steady state oscillation will have a response like this, which is somewhere like negative 35 decibels. Okay, but then if we give it an oscillation that is exactly at the natural frequency of this factor, what happens is that because the oscillation is exactly at the natural frequency, it gets amplified significantly, right? And that amplification depends on how small the damping ratio is. And so if the damping ratio is significantly small, this peak actually should go something like this. Should actually go to infinity if we don't have uh, any damping at all. All right. Erase this and go back. And so also very quickly, again, if this is a pole pair, if we have a zero, a complex conjugate zero pair, right, it would be if we flip basically this, right? Again, if we reflect it with respect to the horizontal axis, we will get the contribution of the second order zero factor. So let me quickly write something here. Okay. So this is the second step. We basically sketch all the individual factors. The third step is that we basically add up the individual factors, right? So let me what I think I need to erase this. This as well. Okay. So we have the gain. Let me also change the template. Okay. So we have the gain at, so this is the gain plot. Let me write this somewhere here. The horizontal line at approximately 30, 13. This is, oh, it's actually 14. Okay. So this is the gain that is equal to like k equal to 5, right? If you take the logarithm with respect to 10 of that, and then you multiply with 20, you will get approximately 14. So this is the horizontal line. This is the first factor that we have in the Bode magnitude plot. And then the next factor is the pole at um, s equal to 0, and again it has a slope of -20. Uh, so I'm not going to write this here because we're going to have to. Where were we? Yeah, so the second factor is the pole, right? And then we have the 0 at which has a breakaway frequency of about 2, so somewhere here. And then we have the pole at s equal to -10. This is the breakaway frequency. The pole pair, which has a breakaway frequency of 15. And then basically sum all the plots on using the blue color. So let me get the blue. All right. So at s equal to 0, we have all the factors contribute almost 0 except for the two, except for the gain and the 0 or the pole at s equal to 0. So 10 plus 14 gives approximately 34, right? And then at 1, again, all the contribution from all the factors is 0 except of the 0 or the pole at s equal to 0, right? So which is going to be which has a slope of negative. I'm sorry. So the contribution of all the factors at omega equal to 1 is 0 except for the gain, right? So we know that at 1 the system passes through the point um, um, 14, right? So now we know that these 2 points belong to the Bode plot, and we also know that between them, the Bode plot has exactly a slope of -20 degrees, thanks to the pole at the origin. So we know that this segment is in the Bode plot, and it has a slope of -20. And it's a good practice to write down these important points. You evaluate at the starting point of your magnitude plot, and then at each breakaway frequency that you come across. Like so this is at point omega equal to 1. This is for the factor at s equal to 0. And then this is the factor at s equal to 1, s equal to 2, and then this is the breakaway frequency for the pole at s equal to -10. And then this is for the factor, the second order factor, and then this is just another point to know where the boundaries of the Bode plot are. Okay, so let's continue. So between 1 until 2 over here, again, the only contribution is from the pole, right? So we continue with a slope of -20. This is just a continuation here. We can also evaluate at omega equal to 2, right? And by evaluate, like I mean to compute basically the gain of the transfer function. So this is the point 1 I. Okay. So if we put 2I into the transfer function, you will get a complex number. To get the magnitude of that, it will be approximately 8. So this point is approximately 8. Now like at omega equal to 2 and starting from omega equals to 2 until the next factor starts kicking in, we have the contribution from the 0, which adds a positive slope, right? That kind of balances the negative slope from the pole at the origin, and so we get a horizontal segment from omega equal to 2 until omega equal to 10. Okay. Then at omega equal to 10, we also know that so this is going to be 10I is going to be approximately equal to 8. And then we get a contribution from the factor at from the pole, right, at s equal to -10. That starts the contribution for that factor starts kicking in, and it'll be the sole contributor, right, because the 0 cancels with because this 0 cancels the effect of this pole in that segment, and so we only have the contribution from this pole, right, which has a slope of -20 degrees. So we see how much that contributes to our plot. So basically we compute at s at omega equal to 50. So this is g of 50I. And if you compute that, you get -6, right? And also there is the contribution from because of damping. So if you compute, you will not get exactly 6. You will get something close to 6, but we can see that the asymptote with a slope of -20 starting from 8 after like not after a decade, but after this much of a decade, it goes to approximately -6. So this is the point we're going to reach, and here's that horizontal line. No, something's wrong. Oh yeah, not this. Somewhere here. Yeah. So this is the line segment. And then finally at s equal to, or at omega equal to omega equal to 50, we start getting the contribution from the slope, which is -40, right? So let's first sketch the slope at -40, which we know that after decades, will go to -40. So this is -20. This is -40. Right. So this is the slope of that vector. We can just continue here. So as I was saying, we have a slope of negative. We already have a slope of -20 here. And so when we add negative 40, you get a slope of -60. Right? So -60 after 1 decade, starting from 50 up to 500. So this was -6. It becomes -66, which is quite large, somewhere here. Chart. So this is the final line when we have well, get the idea. Okay. So this is a slope of -20. This is a 0 decibels per decade. And then -20. And then -40 dp. Right, so the final factor is G of I 500. And this is -66. These are the important slope regions that we were talking about. This is -60. So this is the asymptote, or the asymptote in blue represents the asymptote of the summation of the factors, which is basically the asymptotes that the Bode plot of the system tries to approximate. Don't forget that we need to account for the factor for the damping ratio, which is somewhere here. So this is actually like there's a small deviation here due to the damping ratio. Any questions? Okay. So the phase diagram is pretty much the same. You just have to do put all the diagrams on top of each other on some sketch paper and just do a similar process. It helps to look at what happens at the breakaway frequencies, because they will show you important points that your asymptotes will have to pass through. And also it's important to keep track of the slope regions, because that helps you to know what the graph looks like between these frequencies. Now, these are the basic steps to follow whenever you would like to sketch the Bode diagram. The next example we have for the concept that we're going to discuss are the gain and phase margin. So the gain margin is defined to be the gain margin is defined to be 1 over the gain of the transfer function whenever or at the phase equal to -180 degrees. And the phase margin is defined to be 100 degrees plus the phase at the frequency for which the gain is equal to 0, or 0 decibels, or basically that the gain is equal to 1. These margins come from, or they are clear to see when we have a look on the Nyquist diagram, which we are hopefully going to cover next week, I think. But we can also read them off immediately from the Bode diagram, or we can compute them analytically. So to compute them analytically, we basically need first to find the frequency at which the phase is equal to negative 180 degrees, right? And then we compute the gain at that particular frequency, and the gain margin will be 1 over the gain. And then the phase, we need to compute the frequency, or to solve for the frequency at which the gain is equal to 0 decibels. So let's start with the phase. With the gain margin, which basically means we need the frequency at which the phase is equal to negative 180 degrees. So this is what we have here. Then we can just like substitute with I omega into the factors of the transfer function, and we know that the contribution of the gain k is 0 to the phase, right? The gain does not add anything to the phase. So we have this summation of the phase terms, and then this must be equal to negative 180 degrees. So the phase of this factor is tan inverse of omega divided by 2, right? And then the phase of I omega is just going to be equal to negative 90 degrees, and then minus tan inverse omega divided by 10, minus tan inverse this term here. All of this need to be equal to negative 180. Then we solve using a calculator. Okay. That will give us the frequency, or that critical frequency should be 52 plus 52.5 radians per second. So we compute the gain margin at that particular frequency. It's going to be equal to 20 log 1 over the gain at the critical frequency, which will give us 2.6 decibels. This is the gain margin. The next thing is the phase margin. We set the gain equal to 1, which means that the square of the gain is equal to 1 again, right? So so we just compute the gain in terms of omega. This will give us this equation. Again, we can solve for this using a calculator, and this will give us that the frequency is approximately 41 radians per second. So if we want to compute the phase margin, we compute 180 degrees plus the phase at that particular frequency, which is going to be so like something negative 135 or something like that. So approximately, so it turns out that the phase is going to be like 43.5 degrees. So this is the phase margin. Any questions? Okay, let me go to MATLAB. So I can show you how to do that on MATLAB pretty easily. Right, so okay. So again, this and then RG, which was equal to this. Then we compute Bode plot. Finished. There we are. So yeah, so this is the Bode plot. If we look at the stability margins, first let's look at frequency equal to, yeah. So at a frequency of equal to -500, right? We see that the slope or the magnitude is approximately equal to -66, which agrees with our calculations, right? And at a slope of or at gain of, or a frequency of 50, right? That's when the slope starts kicking in. We should expect here that this is -6 decibels, right? But what happens is that we have a 4 decibels increase, right? Again, this is because of the peak at this particular frequency. It's the frequency equal to 10. We have a magnitude of approximately, the frequency equal to 10, we have a magnitude of approximately 5.38, which is different from what we had. I think we had like 8. Let's see. Yeah, so at omega equal to 10, we expect the frequency equal to 8, or at least the asymptotes tell us there's going to be 8. Again, we're going to have a small deviation, not a large deviation, but we're going to have some deviation. We should expect that. Then, more importantly, at s equal to, or the frequency of 0.1, we see that the plot started as approximately at 34, as we expect. And at a frequency equal to 1, it passes through approximately 14. Right, that's what we computed here. Approximately 14, but we have like an increased decibel, 1 decibel again, because nothing is perfect. But so what happens is that we usually try to like at these breakaway frequencies, these important points, we try to compute the actual gain by substituting into the transfer function and computing the complex number that comes out of it, and then do these corrections to the Bode plot so that we get a better or an accurate Bode plot. So anyways, let's look at the stability margins. So the gain margin, as we said, is is 1 over the gain at the value at the frequency which the phase passes through the negative 180 degrees, right? So we see that negative 180 degrees, the system passes through at omega equal to approximately 52.1. So we go to that point, right? This is the frequency, and we compute the gain at that point. You see that the gain at that point is going to be equal to negative 2.6. So 1 over that is going to give us 2.6, which is the gain margin. Now we look at when the gain crosses the horizontal line that passes through s equal to 0, which happens approximately at 43. We go to the phase diagram. The phase is the phase at this point is what is negative 136 or 37. You add 180 degrees to that, you end up with this phase margin, which is approximately 43. So this concludes our discussion for today. Before we go, does anyone have any questions? All right, thank you guys for your attention.
Thank you.
Thank you.